Greetings, everyone. We've been working with absolute value graphs from tables, but now we're going to change it over to using transformations. Make sure that you have the foldable provided to you in class, and of course, as always, you need your notebook and a writing utensil. Let's take a look at the vertical shift tabs on your foldable. Let's start with vertical shift up. A vertical shift up is represented when the function has a constant added on. For example, if I have the function of the absolute value of x plus 3, that means we shift the graph up k units, or in this particular example, 3 units. Notice again that the addition takes place outside of the parent function, in this case outside of the absolute value. I'm going to relate it back to tables. If we had our table for the absolute value, it would look something like this if I use those standard x values. I want to shift the graph up 3 units. That's going to affect the y values. So we take every y value and we add 3, which means my new y values are now 5, 4, 3, 4, and 5. Let's take a look at how that looks on the graph. 0, 3, negative 1, 4, negative 2, 5, 1, 4, 2, 5. Here is our v. So as you can see, it's the parent function for an absolute value shifted from the origin up 3 units. You can probably already make an assumption for vertical shift down. Let's open that tab. If we subtract a constant from the function, in this case the absolute value, we shift the graph down k units. Let's look at an example of subtracting 3. If we have that parent table, it allows us to clearly see how those values change. Remember, this table came from finding f of x equals the absolute value of x. Now I'm shifting down 3 units. Down affects the y values. So I'm going to subtract 3 from every y value. That now gives me values of negative 1, negative 2, negative 3, negative 2, and negative 1. At negative 2, I'm down at negative 1, negative 1, negative 2, 0, negative 3, 1, negative 2, and 2, negative 1. There is our absolute value graph. It looks just like the parent function, but it is shifted down 3 units at every point. Let's take a look at horizontal shifts. They're going to be very similar to vertical shifts. Vertical shifts were on the outside of the parent function, and they changed the y value. For horizontal shifts, it's going to occur inside the function, or in this case, inside the absolute value. What we have to be careful of is the sign has the opposite effect. So I have subtract 3, but that means I'm going to go right 3 units. Because it is in the function, in the absolute value, we have to think of it as the opposite movement. Let's relate it back to a table. If I have my parent function for the absolute value of x, this is going to affect my x values. I'm going right 3 units. So I'm going to add 3 to every x value. That gives me 1, 2, 3, 4, and 5. Let's take a look at how that looks on the graph. 1, 2, 2, 1, 3, 0, 4, 1, and 5, 2. I can see my parent function has been shifted over from 0 to the right 3 units. Notice in this case, it's the only thing that changed. Everything else stayed the same. Now you can probably make an assumption. If subtracting makes it go right, then adding has to make it go left. That is always the case. So with the example of plus 3, that means that we're going to take our function and we're going to go left 3 units. So if I have my parent table for the absolute value of x, we're going to take our x values and we're going to subtract 3 from each of them, because if I'm going left, that's subtraction on the number line. So we end up with negative 2 minus 3 is negative 5, negative 1 minus 3 is negative 4, 0 minus 3, negative 3, 1 minus 3, negative 2, 2 minus 3 is negative 1. Let's take a look at those values on our graph. Negative 5, 2, 1, 2, 3, 4, 5, up 2, negative 4, 1, negative 3, 0, negative 2, 1, and negative 1, 2. We can see how our parent graph was affected very clearly. We went to the left 3 units. Let's talk about vertical compression and vertical stretch. If I have a value out front of my function, so in this case, a is out front of f of x, so we're multiplying. If the value is between 0 and 1, it multiplies the y values of that graph by the factor of a. So that makes sense. It looks like I'm taking a times f of x, and that's exactly what I'm going to do. Now, if I'm using my tables, it's affecting my y values. Let's take a look at an example. It's on the outside of my absolute value, which is why it's affecting the y values. So in this example, let's use our parent table again. Now these parent tables are so important because we're going to use these tables for so many of our graphs. And when we combine all of these rules, it makes it so easy to follow. So we're going to take our y values and we're going to times them by a half. Which gives me a new y value here. 2 times a half is 1. 1 times a half is a half. 0 times a half, still 0. 1 times a half, half. And 2 times a half is 1. Let's see how this graph looks. We have negative 2, 1. Negative 1, half. 0, 0. 1 half. And 2, 1. See how it looks like it widened our absolute value? We call that a vertical compression. It's compressed that V down. It's almost squished it and widened it. So again, when you have a value being multiplied out front, you multiply all the y values by that. Let's take a look at vertical stretch. With a vertical stretch, it's the same idea. You have your a value times your function, but this time a is going to be greater than 1. So let's look at this example of 2 times the absolute value of x. Let's start off with my parent table. Again, I'm going to stress this. The parent table just means we're graphing y equals the absolute value of x. If I plug in these x values into that function, I get these y values. So I'm going to take every y value and times it by 2. I end up with a 4, a 2, a 0, a 2, and a 4. If I plot these new points, -2, 4, -1, 2, 0, 0, 1, 2, 2, 4. Take a look at how this graph looks now. It looks skinnier than our parent function. The graph grew taller. There's a couple of ways you might want to describe it. Taller, skinnier, but most importantly is we want to go back to the fact, is it a compression or a stretch? So it's going to take a little while to learn those words. Let's take a look at the last 2 tabs on your foldable. Reflection over the x-axis. If I reflect or mirror my graph over the x-axis, it's like we're flipping it down or up. This occurs when I multiply the function by a -1. So even though we write it as negative f of x, what we're really doing is saying -1 times f of x. Again, this reflects it over the x-axis. Let's take a look at this example. The negative, notice, is outside of the absolute value. So when I have my parent table, we have to decide, am I going to multiply the x's or the y's by that negative? If it's on the outside of the absolute value, outside of the parent function, it affects the y values. Just like the number outside affected the y's. The signs outside affect the y's. So I'm going to take every y value and times it by -1. And we'll end up with these values. Let's prove how this is true. If I graph it, I'm at -2, -2, -1, -1, 0, 0, 1, -1, and 2, -2. Here you can see that that worked. I now have my parent function of the absolute value flipped or reflected over the x-axis. So it flips it up or down. Here's a little hint. Let's say we forgot and we accidentally multiplied the x values by -1. If we did that, it wouldn't flip it. So we would know that something's not right because it didn't flip. Now that we've looked at these horizontal shifts, vertical shifts, reflections, vertical stretch, let's tie it all together into one example. If I have the function 2 times the absolute value of x minus 1 minus 2, notice that I have 3 moves, the 2, the -1, and the -2. Let's start with our parent table. I'm going to leave a little bit of space here because I'm going to do a little bit of work. Here's our parent table for the absolute value of x. Now, when you're looking through this equation, we want to go in order. We start with the 2, then the -1, then the -2. We read left to right. The 2 on the outside is being multiplied. If it's on the outside, it affects the y's. So we're going to multiply every y value by 2. Then subtracting 1 is on the inside, so it's going to affect my x's. Now remember, this horizontal shift, the opposite occurs. So even though it says subtract 1, we're going to add 1 to each x value. This next move of subtracting 2 is on the outside of my absolute value. The outside means it affects the y value, so I'm now going to subtract 2 from every y value. Let's take a look at what our new table would look like. On the left side, -2 plus 1, -1 plus 1, 0 plus 1, 1 plus 1, 2 plus 1. On the right side, 2 times 2 is 4, 4 minus 2, 2. 1 times 2 is 2, 2 minus 2, 0. 0 times 2, 0. 0 minus 2, -2. 1 times 2 is 2, 2 minus 2, 0. 2 times 2 is 4, 4 minus 2 is 2. Let's see how this graph looks. -1, 2, 0, 0, 1, -2, 2, 0, and 3, 2. We can see our V, it's perfectly symmetrical, which is what we needed. So let's talk about how this absolute value graph moved, how it transformed. We multiplied the y values by 2, we shifted right 1, and we went down 2. Does that make sense? If I start at the origin, I went right 1, down 2 for my new vertex. And then the times 2 made it skinnier. Now that we've completed our foldable, one of my recommendations is to rewatch this video. I'm sure as you were watching it, you were also writing. Sometimes we gotta slow things down and only do one thing at once. So take some time if you're a little confused to just rewatch it. Don't write anything, don't get distracted, just watch. Be prepared, because now we're gonna take one graph of an absolute value. And we have so much information. We can talk about domain, range, increasing, decreasing, maximums, minimums, vertex. Now we can talk about horizontal shifts, vertical shifts. We can talk about compressions and stretches. So many factors, more than that even, affect one graph. So again, we're going to have one graph with so many questions and point values to it on a test. So take your time, review our previous concepts if needed, so that you're prepared to combine these ideas. Again, take some time to rewatch. Good luck, and we'll see you next time.